So now let's go over our practice problems dealing with colligative properties. So in the first question, I want you to find both the freezing point and the boiling point for the same solution. And that's a solution that contains 100 grams of sodium chloride dissolved in 5 liters of water. So this will end up being pretty straightforward because the main thing here is calculating the molality. And since we're using the same solution for both, we only have to do that calculation once. So molality, recall, is the moles of the solute. So that's the 100 grams of sodium chloride converted to moles. That right there will give us our moles of sodium chloride divided by the mass of the solvent in kilograms. Water, recall, is 1 gram per milliliter or 1 kilogram per liter. So that 5 liters becomes 5 kilograms. And we get a molality here of 0.34 molal. From there, we can calculate our changes in freezing point as well as our changes in boiling point. In each case, we use the appropriate constant, so that's Kf for the freezing point. And for boiling point, that's the Kb. We need to multiply those by the Van Hoff factor, remember the number of ions. So given this is sodium chloride, this will split into a sodium and a chloride ion. So our Van Hoff factor here is 2. And then times the molality. Again, since we're looking at the same solution for both freezing point and boiling point, we have the same molality in both calculations. So our change in freezing point is 1.27 degrees Celsius, and our change in boiling point is 0.35 degrees Celsius. So notice, and I think this is an important thing to notice, that making solutions has a larger impact on the freezing point than they do on the boiling point. Now that shouldn't be a surprise given that for water here especially, the Kf is much, much larger, almost 4 times that of Kb. But we're not quite done here, because the question I've asked is what will be the freezing point and what will be the boiling point, not what's the change. So we need to then factor these in to the normal boiling points as well as freezing point. So the normal freezing point for water is of course 0 degrees Celsius. So the new freezing point will be 0 minus the change, or negative 1.27 degrees Celsius. And the new boiling point will take the normal boiling point of water of 100 and add in the 0.35 to get to 100.35 degrees Celsius. All right, question 2, we're looking at something a little bit different. So now I'm saying we're going to take ammonium phosphate and we're going to add it to 500 grams of water, and we want to make the new freezing point 8.3 degrees Celsius. So the question becomes, how much of it do we need to add? So we know that our change in freezing point is equal to Kf times I times the molality. Now, which of these do we know and which of these don't we know? Well, we know the change in freezing point because we want to lower it to negative 8.3 degrees Celsius. So we know the change would need to be 8.3 degrees Celsius. The Kf value for water is something that we can look up. We find it in the previous problem. It has a value of 1.86 degrees Celsius per molal. Now, what is I in this case? Well, in order to know what I is, we need to know the formula for ammonium phosphate. So ammonium phosphate, NH4 is the ammonium ion, has a +1 charge. Phosphate is PO4 3-, so we need 3 ammoniums and 1 phosphate. That means if ammonium phosphate completely dissociates, which we say that it does here, that we would get 3 ammonium ions and 1 phosphate ion. So therefore our Van Hoff factor here is equal to 4. What's the molality? Well, we don't know. And that's the entire point, is that we're asking how many grams do we need. So the molality here is our unknown. So we can solve this equation for x, and we get that in order to lower this solution by a total of 8.3 degrees Celsius, we need a concentration of 1.12 molal. Not done though, because this is just the molality. We're looking for the grams of ammonium phosphate. So molality is equal to the number of moles, which again we don't know, over the mass of the solvent, which is 500 grams or 0.5 kilograms. And so we know then that X is equal to 0.56 moles. So finally, the last step is that we need to convert this to a mass of ammonium phosphate. In order to do that, we need to know the molar mass. We can add up the elements in the chemical formula. We get 149 grams per 1 mole. And so we find out that we need 83.4 grams of ammonium phosphate. All right, so our last two questions here deal with the type of situation we often use as a lab experiment. And in both of these questions, we have a solution that we've made up. We've added an unknown solute to it, and it's changed the freezing point of our solvent. So the way you would do this if you were doing this as a lab experiment is you would take your pure solvent and you would measure very carefully its freezing point. Then you would melt the pure solvent, you would add your solute to it, and then slowly cool it down until it froze again. And then you could find your two freezing points, you'd take the difference, and that would let you calculate the molecular weight. So that's the data that's presented here as if we had done that experiment. So what we know here and what we don't know here are, we know the change in freezing point, we know the constant, and we can determine the Van Hoff factor. So what we don't know is the molality. So the change in freezing point here is the difference between the normal and the other freezing point. And we can just calculate that difference as 2.01 degrees Celsius is equal to the Kf value for the solvent. For the solvent here, the solvent is benzene, 5.12 degrees Celsius per mole. Now, what do we do for the Van Hoff factor? Because we don't know what the unknown is. Well, recall during lecture, our previous lecture, or our previous video, that we said that if we're dealing with an organic solvent, especially a hydrocarbon, and benzene being C6H6 certainly is a hydrocarbon, then what we find is that we're not going to have ionic compounds in those solvents. And so we can make the assumption that our Van Hoff factor here is 1. And the molality is unknown. So we can solve this for molality. And that is equal to 0.39 molal. Now, as we've seen in the past, if we want to figure out molecular weight, we need to know grams over moles. Well, we know the grams of the unknown, that's given. Now that we know molality, though, if we know the mass of the solvent, which is given as 100.2 grams or 0.1002 kilograms, we can figure out the number of moles. And so X is our number of moles, is equal to 0.039 moles. Finally, we can calculate our molecular weight as the mass that's given, 5.782 grams, divided by the number of moles we just calculated, 0.039 moles, and we get a molecular weight of 148 grams per mole. Our fourth problem on this sheet is very, very similar. The only thing that really changes here are the amounts and the identity of the solvent. So we're going to go through the exact same steps, and we find the difference in the freezing point between the pure solvent of 76.2 and 80.6. Gives us a difference of 4.4 degrees Celsius. The Kf value is given here as 6.9. Again, because we're dealing with an organic solvent, a hydrocarbon, we're not going to have an ionic solute, so we can assume the Van Hoff factor is 1 times the molality. So our molality here is 0.64 molal. Again, we can use that 0.64 molal is equal to the number of moles over the mass of the solvent, 0.014869 kilograms. So our number of moles is 0.0095 moles. Finally, to find the molecular weight, we just need to take the mass of the solute, 1.324 grams, divide that by the moles that we just calculated, and we get the molecular weight of 139 grams per mole.